MES College Marampally, e-learning.
Dear students, I am Peter Kevu, Associate Professor, Department of Mathematics and Statistics, MES College Marampally. Today, I am going to deliver a speech on a very important and elegant result in group theory, none other than the Lagrange's theorem. It is a basic result in group theory and it has got applications at various levels. We shall now discuss the theorem in detail. So, over to Lagrange's theorem on finite groups. As prerequisites to describe this result, we recall the concepts of partition of a set, equivalence relations, fundamental theorem of equivalence relations, equivalence of finite sets, and relevant other results. Which are applicable here. We all know that a partition of a set is a collection of its subsets whose union is the full set and their pairwise intersection is empty. That is a partition. If you want to represent a partition as a diagram, suppose A is a set like this. We can describe a partition of A simply by dividing it into several parts like this. You can see that here there are 1, 2, 3, 4, 5, 6 and 7 subsets. As it is shown in the diagram, their union is the full set A, and if you take the intersection of any two of them, you can see that they are pairwise disjoint. So, that is a partition. What are equivalence relations? The second point, we know that an equivalence relation on a set A is simply a relation which satisfies three properties. One, it is reflexive, then it is symmetric, and it is transitive also. Such a relation we call an equivalence relation. The third point is the fundamental theorem of equivalence relations. You might have heard about this particular result in algebra. According to this theorem, if R is an equivalence relation defined on a set A, then R partitions it into mutually disjoint equivalence classes in such a manner that Elements from the same class are related and elements from different classes are not related. On the other hand, that is conversely, every partition of A describes an equivalence relation of the set. So, that is a very powerful theorem in algebra and that is useful in our context of discussion of Lagrange's theorem. The next point is equivalence of finite sets. We all know how to make two sets equivalent. Suppose A and B are two sets, then A and B are equivalent. We say that they are cardinally equivalent if there is a one-to-one correspondence between A and B, that is, there is a bijection of A onto B. Here in this context, we consider finite sets. Suppose A and B are two finite sets, and if there is a bijection between A and B, then according to the theory, we can say that the number of elements in A and B must be equal, and that is a wonderful result which is used in the context of proof. The last one, some relevant results from other sections. For example, for number theory, we make use of a simple relation known as divisible by or divides. This is a simple relation in the set of integers z defined by A divides B if B is expressed as a multiple of A. A divides B if B is expressed as a multiple of A, that is an integer k into A. Then we say that A divides B. Then this relation divides is also used in our present context of the proof. So, these are simply some prerequisites which are used in the context of a proof. Now, over to the proof of the theorem. We are going to mention two or three simple results in groups. Let G be a group. H is a subgroup of G. This is a symbol used for subgroup. H is a subgroup of G. Let us describe a relation on G by setting A is left congruent to B mod H. You can read it as A is left congruent to B mod H if and only if A inverse B belongs to H. If and only if A inverse B belongs to H. It's a very simple relation. All of you can easily verify that this relation satisfies reflexivity, symmetry as well as transitivity, and hence it is an equivalence relation. The proof is very simple. I am not going to discuss these points here. In a similar manner, I can set another relation. A is congruent to right congruent to B mod H. If and only if A B inverse belongs. That is, the position of the inverse is going to change. This is, in this case it is A, and in this case this is for B. And this is also again an equivalence relation. Now, all of you know that Equivalence relations has got a wonderful property, namely, it will partition the set. What is the set under consideration? The group G. This group G can be partitioned into mutually disjoint equivalence classes by using this relation as well as this relation. Take any one of them and think of its partition. We are going to recognize a typical equivalence class of this particular equivalence relation. That is our task now. Anyway, by using our basic definition of an equivalence class, all of us know that if R is a relation, then the equivalence class of A is nothing but the set of all x belongs to A such that x is related to, or A is related to x. That is, find out the points in X which are related to the single point A, and that is our equivalence class of A. And here this left congruence modulo H, this is found to be an equivalence relation on G. Let us see a typical equivalence class of that particular equivalence relation. Now, before finding the equivalence class of A, I am going to introduce the notion of a coset. Notion of a coset, and later I will connect the cosets with equivalence classes. That is my task. So, first of all, I will introduce a coset. Here G is a group, G is the group, H is the subgroup of G. I want to introduce the cosets of H in G, cosets of H in G. Look, the left coset of H in G containing the element A belongs to G is given by AH equals set of all AH, H belongs to H. So, a very simple definition. See, this is a left coset of H in G containing the element A. Here this A is nothing but a representative, because we are going to relate this cosets with equivalence classes, and this in this equivalence class this A is nothing but is a representative, and you know that in the case of an equivalence class, every member of the equivalence class can have the property of being a representative. So, here H is equal to set of all A small h, H belongs to H. Similarly, I can define a right coset. Right coset has got notation HC, that is the position of A gives whether it is right or left. So, the right coset of H in G containing A is put in a equivalent form EHA, H belongs to H. So, these are the cosets. Next task is to relate cosets with equivalence classes of that particular equivalence relation which I told you, that is the left congruence modulo H as well as the right congruence modulo H. Okay. We are going to write what actually an equivalence class of A of the equivalence relation left congruence modulo H. What is left congruence modulo H? We have just seen that A is congruent, left congruent to B mod H if and only if A inverse B belongs to H. That you will see. Here, this is the equivalence class of A. So, let us write what is equivalence class of A. By definition of equivalence class of A, it is a set of all elements of the set under consideration, that is the group, which are related to the single element A. Here, it is a set of all x belongs to G. G is the full group such that A is left congruent to x mod H. What does it mean? A is left congruent to x mod H. What is the meaning? According to the definition of that particular congruence relation, this relation, equivalence relation, what does it mean? A is left congruent to x mod H if and only if A inverse x belongs to H. That is if and only if, look, A inverse x belongs to H happens only when x belongs to H, because A inverse x belongs to H means we can write A inverse x is equal to small h, where H belongs to H, which implies by left multiplication, pre-multiplication of A yields x is equal to AH. And now in this AH, we have already seen that this AH is a typical member of the left coset of H in G, and that is AH. A capital H is the left coset of H in G containing A. So, look, see what actually we established. A is left congruent to x modulo H if and only if x belongs to AH. If and only if, that is, if x is in AH, relation is okay. If the relation is okay, then x belongs to AH. So, what is actually AH? AH is simply the equivalence class. So, what we recognized at this moment is nothing but the equivalence classes of this left congruent modulo H are precisely the left cosets of H in G. Similarly, take the other relation, that is the right congruence modulo H. What will be the equivalence classes of such an equivalence relation? They are precisely the right cosets of H in G. So, this is actually the relation between the equivalence classes of this particular equivalence relation and cosets. Okay. Thus, we have seen the relation between equivalence classes of A and cosets of H in G containing A. We are now going to establish another result which are used in the proof of Lagrange's theorem, and that is nothing but take two left cosets of H in G, say AH and BH. Look, here H is a, remember, H is a finite subgroup, G is a finite group and H is a subgroup of G. I am talking about only cosets containing finitely many elements. So, that G finite group, this is a special case, H subgroup of G, therefore, H is also finite. Let us see two such left cosets of H in G. Now, since we have seen that these left cosets are nothing but equivalence classes, these left cosets must satisfy the property of equivalence classes, because equivalence classes describe a partition of the set, or if R is an equivalence relation, it will partition the set into disjoint equivalence classes. So, we have already established that the group G is actually a union of mutually disjoint left cosets as well as right cosets. That actually we did. But what about the number of elements in each of these left cosets of H in G? I can prove that the number of elements in these two cosets are actually equal. I can easily prove by establishing a one-to-one correspondence between this set. Remember, here G is a finite group and H is a subgroup of G, and so H must be finite. Hence, AH and BH are of finite cardinality. Now, instead of proving AH and BH, between them there is a one-to-one correspondence. I choose AH as it is, but instead of BH, I take EH, because EH is also a typical coset generated by or containing the element E, or where E is the representative. And what is EH? E is equal to H itself. So, in order to establish a relation, equivalence between AH and BH, I will find out a one-to-one correspondence between AH and EH, or AH and H itself. For that, I define a function phi from H to AH by setting phi of H is equal to AH. H belongs to H. I can easily recognize that this is a well defined rule, this is one to one and this is on to. See the proof. Take H1 and H2. Suppose H1 is equal to H2 in H, then AH1 is equal to AH2, implies phi of H1 is equal to phi of H2. So, very simple to understand. See the steps. H1 and H2 are equal, then by left multiplication of AH1 is equal to AH2, but AH1 is phi H1 and AH2 is phi H2. So, phi H1 is equal to phi H2. What does it mean? This shows that the rule phi is well defined. See the converse. Suppose for H1 and H2 belong to H, phi H1 and phi H2 are equal, then AH1 is equal to AH2. Now, A is a common factor, or you can apply the left cancellation law to cancel off A. We will get H1 is equal to H2. So, we can apply the reverse implication also. Hence, phi H1 equals phi of H2 implies AH1 is equal to AH2, implies H1 is equal to H2 by left cancellation law. And what does it say? This means that phi is 1 to 1. This means phi is 1 to 1. So, 1, phi is well defined, 2, phi is 1 to 1. Finally, we can show that this phi is on to also, that is corresponding to every point in the codomain, I can find an inverse image. Suppose AH is a typical element here, and I can find a typical pre-image, and that is nothing but H itself, as it is clear from the definition, because H is a member of AH coset. H is its inverse image because phi of H is equal to AH. So, the function is necessarily onto. So, the function is well defined, 1 to 1, and onto. Since phi is 1 to 1 and onto, it must be a bijection. So, phi is a bijection. Now, look, H as well as AH, the domain and the range, both are finite sets, because H is a subgroup of the finite group, means H is finite. So, the cardinality of H and cardinality of AH both are finite, and between H and AH we established a bijection or a one-to-one correspondence. So, what can you conclude? We can conclude that their cardinalities must be equal. What does it mean? Their cardinalities must be equal. What do you mean by the cardinality of a finite set? The cardinality of a finite set is nothing but the number of elements in it. So, the number of elements in H is equal to number of elements in AH. Now, instead of AH, if I take say BH, what I get? I get cardinality of H is equal to cardinality of BH. So, cardinality of AH and cardinality of BH must be equal, which I am looking for. So, AH and BH, if there are two left cosets of H in G, what I established at the moment is they contain same number of elements. They contain same number of elements. Finally, we come to our celebrated result, the Lagrange's theorem. Statement. Let G be a finite group. And H subgroup of G. Then order of H is a divisor of order of G, or in symbols cardinality of H divides cardinality of G. Remember, here G is a finite group. So, both order of H, cardinality of H and cardinality of G are finite quantities, and cardinality of H must divide cardinality of G, and divides is a relation. I told you previously, divides is a relation from number theory. We are all familiar with such a relation, and Lagrange's theorem is a occasion or an area where this number theory result finds an application in algebra. That is, number theory in which divides is used for several things, and here this divides relation is used here in group theory in the context of Lagrange's theorem. To prove this theorem, we first consider the group G finite and its decomposition into mutually disjoint left cosets of H in G. Here H is a subgroup of G. So, naturally the left cosets of H in G can be considered. According to our theory that we developed, we have seen that this particular G can be partitioned into mutually disjoint equivalence classes, and each typical equivalence class is a typical left coset. Hence, corresponding to that partition, we can call it a left coset decomposition. We can consider G as the union of mutually disjoint left cosets of H in G. Therefore, consider G as the union of mutually disjoint left cosets of H in G. Why this is possible? Because we have already established that these left cosets form a partition of G, and that comes from the property of the equivalence relation, or by using the fundamental theorem of equivalence relations. Okay. So, I can have a very simple diagram in this context. Look at the group G. This is G, and I am going to partition it. Say this is one coset, this is another one, this is a third one, this is a fourth one, this is a fifth one, a sixth one, seventh one. So that altogether they are 1, 2, 3, 4, 5, 6, 7, 8 cosets. And any two of these cosets, if you take, they are mutually disjoint. See, mutually disjoint. What about their union? Their union is all of G. So, this is AH, this is BH, etc. Look, let us now suppose that there are distinct left cosets are there are distinct left cosets. Also, take order of H is equal to say M, and order of G is equal to N. Look at the situation. We have established that the number of elements in AH is equal to number of elements in BH, that we have already found. Now, here H is a typical coset which comes in this collection. So that the number of elements in AH, BH, CH, etc., any coset is equal to the number of elements in H, because H itself is a coset. Therefore, the number of elements in G, the number of elements in G equals, look, you have to count, you can just count, you can add the number of elements in various cosets, first coset, second coset, etc. How many cosets are there in total? There are R cosets, and each coset has got as many elements in as H. In H there are M elements, so in AH there are M elements, in BH there are N elements, in any other coset there will be only M elements. Since there are R such cosets, what is the total number of elements in G? R times the number of elements in M, that is R into M. This is simply by using this particular partition. This partition comes from the decomposition of G into left cosets. So, we make use of the left coset decomposition, we can say that it is a left coset decomposition of G into mutually disjoint left cosets of H in G. Suppose there are such distinct left cosets, and order of h is equal to m and order of g is equal to n, you will be able to write the number of elements in G that is equal to n is equal to r into m, where m is the number of elements in H. What does it mean? This means that m divides n. That is, m is a divisor of n. What is m? Order of H. What is n? Order of G. So, we arrived at the required result. Order of H is a divisor of order of G. Hence, the theorem of Lagrange is established. See once again, what is the Lagrange's theorem? Lagrange's theorem says that G is a finite group and H is a subgroup of G, then order of H is a divisor of order of G. There are two immediate corollaries for this particular theorem, which finds several applications in our further studies in groups. One is, you take any group of prime order, any group of prime order. Any group of prime order must be cyclic. Any group of prime order must be cyclic. It's a very interesting result, because this is an immediate application of Lagrange's theorem. So, wherever you find a group of prime order, it must be a cyclic group. All of us know that what is a cyclic group. A cyclic group is a group generated by a single element, and it has got wonderful properties. So, in the context, we can easily prove that by using this Lagrange's theorem, we can easily prove that any group of prime order is cyclic. And another corollary is the order of an element of a finite group is a divisor of the order of the group. This is also a very useful result. The order of an element, we know what is the order of an element. The order of an element A is the least positivity n such that A raised to n is equal to E, the identity element of the group. So, order of an element of a finite group must be a divisor of the order of the group. This also can be established easily by the Lagrange's theorem, and we are now ending up our session by introducing the possibility of the converse of the theorem. That is, whenever we establish a result, we naturally think of its converse. Here, the Lagrange's theorem states that order of the subgroup of a finite group is a divisor of the order of group. What about the converse? Suppose order of G is there, we take the divisors of order of G, can we get subgroups of every such level? That is, if M is a divisor of N, can there be a subgroup of G of order M? It is a very interesting thing, and unfortunately the converse is false. We can point out an example. A very good example available is the group A4. A4 is a group, you are all familiar with this group. This is the alternating group on 4 simples, and what is its cardinality? its cardinality is half of the cardinality of S4. What is S4? S4 is the symmetric group on 4 simples. It has got a cardinality for factorial is equal to 24, and so the value is 12. So, A4, the alternating group, the group of all even permutations on 4 simples, contains 12 permutations, and suppose G is this group. Then, what are the factors of order of G? Factors of what are the factors of order of G equals 12? What are the factors of order of G is equal to 12? They are 1, 2, 3, 4, 6 and 12. These are all factors of 12. 1 divides 12, 2, 3, 4, 6, all are divised 12 itself. All are divisors of 12. You can just remove 1 and 12 because they are improper divisors, trivial divisors, because this corresponds to the singleton set and this is the full group. Take the cardinality levels 2, 3, 4 and 6. By actual calculation or computation or looking at the structure of A4, one can easily find subgroups of order 2, subgroups of order 3, subgroups of order 4, but subgroups of order 6 are not there. What does it mean? If you take any combination of 6 elements from this A4, you cannot form a subgroup. And you can try as an exercise, you can try that any 6 elements of A4 never form a group. What does it mean? It shows that A4 has got no subgroup of order 6, whereas 6 is a divisor of 12, the order of the full group. What does it mean? This shows that the converse of Lagrange's theorem is false. It's a very simple example. So, Lagrange's theorem, which states that the order of the subgroup of a finite group is a divisor of the group, is proved here. We also considered 2 simple corollaries of this result, and finally we found that when we consider the converse of Lagrange's theorem, we can easily show that the converse of Lagrange's theorem is actually false by pointing out an example of A4. And this is all about today's sessions. Hope that you have understood very well Lagrange's theorem and its consequences. Thank you very much.